Hey guys, in this video I'll be introducing you to parallel computing on GPUs and we'll be writing our first program. CUDA is a parallel computing platform and application programming interface model created by NVIDIA. It allows programmers to use NVIDIA GPUs for general purpose processing, an approach termed general purpose computing on GPUs, in short GPGPUs. And it's specific for NVIDIA GPUs. So why CUDA? If you go over to julialang.org, read all that, come down, go to parallel computing, read that. Over here it says the Julia compiler can also generate native code for various hardware accelerators such as GPUs. And it says generate native code. Go here and it takes you to a GitHub repository of a package called CUDA which and it says Julia support for native CUDA programming. So Julia is providing support for native CUDA programming. Just Google CUDA and click on the first link that opens other than Wikipedia. You'll see CUDA is a parallel computing platform and programming lab model developed by NVIDIA for general computing on graphical processing units (GPUs). With CUDA, developers are able to dramatically speed up computing application by harnessing the power of GPUs. So it is CUDA that allows us to harness the power of GPUs and not Julia in turn. So what it does, what's happening here is Julia support for native CUDA programming. In the sense, Julia compiler can also generate native code. So you write Julia code, which in turn is converted into CUDA code by the Julia compiler. So what can be done with Julia is limited by what can be done with CUDA as of now. Okay, so today we'll go to some basics of file programming. What's a host, device, a kernel, threads, blocks, grids. We'll go to all of them. Commonly, the CPU is called the host and GPU is called the device, as simple as that. Nothing much to explain over there. Both host and the device have their own memory called host memory and device memory. This is pretty important. And all the code we write to run parallelly in a GPU comes inside a special function called the kernel. This kernel is different from the kernel in operating systems. There it means a central part of the operating system itself. Here, kernel is just a set of instructions which can be run on the GPU. Okay, now with all the above jargon, let us look at some of the typical sequence of operations in a CUDA program. Yeah, CUDA, because that's what we are actually doing. So first you will declare and initialize host data. Host data in the sense data that is present on the host memory, which is usually the input which we deal with. Next, you'll have to transfer the data from host to device because the device can't access host memory and host can't access device memory. And then we'll call a kernel function to operate data on device. So the GPU performs the computations. And then you'll transfer the result back from device to host so that the host can do something further with it. Note that all the code is in the host memory and the entire program is run on the host. That is, we run the program on the host. And when a kernel function is called, the necessary data and instructions are sent to the device by the host. It is like a master-slave setup with the host being the master and the device being the slave. Okay, so as mentioned earlier, the kernel is run parallelly on the GPU. Each unit of computation on the GPU is called a thread. So each thread independently and parallelly runs the kernel code. As for an array, we have index to access a memory location in CUDA. Each thread has its own set of indices to identify each thread from each other. This gives rise to a hierarchy of grids, blocks, and threads. Okay, all threads running in a kernel belong to a grid. The grid can be further decomposed into a number of blocks. Finally, each block consists of threads. Thus, a thread in CUDA has three indices. So it's like there are threads, the set of threads make a block, and few blocks make the grid. And the indexing goes like for thread index, we can uniquely identify the thread within a block, and the layout of the threads can be 1D, 2D, or 3D. Like all the threads can similar to an array. Like the threads can be accessed in 1D or 2D or 3D. Similarly, the block index is used to identify a block within a grid, and the indexing can be done in 1D, 2D, or 3D, and same for a grid. The above thread hierarchy has been introduced to map the data to be processed to threads. The data which we usually process are in the form of arrays, which can be either 1D, 2D, or 3D. So it's easier to map a thread to a data unit with the help of the following hierarchy. It's helpful in some cases, and you'll find out soon. This hierarchy can be better understood when you view them from the hardware perspective. This is a neat image. A thread which we are talking about is executed by one core. A set of thread which is known as block is executed by streaming multiprocessor, which contains a set of cores. And the entire kernel grid which we launch consists of several blocks, is executed by the compute GPU unit. Okay, so then when a kernel is launched, the number of threads per block and the number of thread blocks is specified. This in turn defines the total number of CUDA threads launched. So while launching the kernel, we specify how many threads are going to be there and how many blocks are going to be there. The maximum X, Y, Z dimensions of a block are 512, 512, and 64. And it should be allocated such that X, Y, Z less than 512. This is not strictly 512, it depends on the GPU we're talking about. Modern GPUs can take up to 2048, and the ones on Collab can take up to 1024. So I just change that to 1024, which is the maximum number of threads per block. Blocks can be organized into 1 or 2 dimensional grids of up to 65,535 blocks in each dimension. The limitation on the number of threads in a block is actually imposed because the number of registers that can be allocated across all threads is limited. You'll understand all of this later. This is just another neat diagram. You'll understand all of this better when we start coding. So let's head over to Collab. So these are the installation instructions I'd sent you previously. Let's start off by connecting, and since I'd run this entire thing before, now I'll just have to run this second thing which installs Julia. And running it is, I forgot to mention before, it's just Control plus Enter or Shift plus Enter. Control plus Enter will run the cell and keep you in the same cell, whereas Shift plus Enter would run it and take you to the next cell. So the cursor comes all the way over here. Now this is going to take some time, so I'll just skip that. So once it's done, go to New tab, open Collab over there, go to File, Upload Notebook, Browse, select the file which I had sent, wait for it to upload, and you get a new notebook. Let's just rename this first, JuliaGPU intro. That should work. First, adding the packages which we're going to need using the package manager. So it'll be pkg.add. I'll just select this. I'll be needing 3 packages. First one is CUDA native. Second one is CuArrays. Third one is CUDA driver. No need to fret about what you'll be doing. You will get to know about those later. The first one is going to take time because Collab is going to start connecting, initializing, allocating and stuff. So that, and then using CUDA native, CuArrays, CUDA driver. This first run is gonna give you an error probably, and yeah, this, it's harmless. It's a issue which has been fixed in version 1.1, but it's going to stay for some more time in version 1.0. Just running the same thing again would just remove the error. With that, let's write our first kernel. Yep, it's hello world. And then, so I told you that you could identify each thread and deal with just that thread. The way you do this thread ID x of dot x would return its ID along x direction, so TIDX, thread IDX. Similarly, we have thread ID along y direction and TIDZ equals thread IDX of z. And let's just print the identity of each thread. So the way you print is by using the macro coprintf, not println as you used to do in the host. This is a call to the CUDA API. And in here you'll be writing mostly like C. So I am thread percentage %LD percentage %LD percentage %LD. Also, always use percentage %LD because percentage %T gives random errors. I don't know why I haven't been able to fix that yet. TIDX, TIDY, TIDZ. And that should be the first kernel. And by I haven't been able to fix that yet means it's a known issue, the abnormality of coprintf with percentage %T. So let's call the function now. Hello world. Nope, it's an error. Hello world is not defined. Why? Because this is a kernel function and we can't invoke it normally. We have to do at CUDA. This informs that. So let's call the function hello world. And if value hello world not defined, oh, I forgot the braces. So let's just run it again. And you get your session crashed automatically restarting. What basically happened is this was a kernel program and you ran it as a normal function. So you can't do that. You have to inform the compiler that it is a CUDA function. So you have to use the macro at CUDA before running it. Now, since the session restarted, I'm going to have to run all of these again. Not this one, the packages will still be there. I'll just run this, and this one. Yeah, this one's still going to throw an error now. That's completely fine. Kernel returns a value of type. Yep. Every kernel function should end with a return or a nothing or a return nothing. So we get the output. I am thread 111. But why just one thread? Because while launching the kernel, we didn't specify about the number of threads. So by default, it's just one. So the way you do that is by doing this, threads equals 5. So you do that, you'll get thread 1, 2, 3, 4, 5. Now you can see that only the X is changing because by default, when I say threads, it's just a 1D. Now if I make it 2, 3, you can see 1, 2, 2, 1, 1, 2, 2, 2, 1, 3, 2, 3. So now it's a 2D. And if I make that further 2, which should totally launch 6, 12 threads in all. Yep, you're getting it. You might wonder why this order of printing. It's just that when the kernel is launched, we can't guarantee anything about the order of the threads. Like any thread might run first, any thread might finish before the other. There's no guarantees about what would happen. So as a good practice, it's good to synchronize every kernel call so that the host waits for all of the threads to finish. For now, you'll just be getting the same output again. Okay, so now let's launch a random number of threads, 1,000 threads. See, we get the output. Let's make it 2,000, and you get an invalid argument. Invalid argument because if you remember, I said there's a limit on the number of threads you can launch, which was 1024. It still works. You make it 1025, and it says invalid argument. So now, what if I still want to launch 2,000 threads? You can do that by launching another block. Blocks equals say 2. So threads equals 500. So totally this will launch 200, 1000. When you didn't mention blocks was default to 1. You can check this by just say 5. You'll get two same outputs. This is because this is of the thread in the first block, this is of the thread in the second block. So now how do I differentiate between these threads? Similar to how you did for thread ID, you can do for block idx equals block idx of dot x. And let's just print that one too. Percentage LD, comma bidx. You see, this is from the second block, this is from the first block. Okay, so few points to note now. When this kernel is launched, this entire code is executed by all the threads parallelly at the same time. And there's no guarantee on which will execute first, which will execute second, which will finish first. It's random. And another thing to notice is I did tidx equals. So any variable you declare inside the kernel is private to that thread. So each thread will have its own tidx. Similarly, each thread will have its own bidx. Each thread will do this, and so on. And any parameters passed to the function will be common to all the threads and all the blocks. And there's another thing called, so this thing is called local memory because it's local to a thread. Any parameters passed are called will be in the global memory because it's common to everyone. And there's another thing called shared memory wherein a set of variables is shared between one block. So these 5 threads would be sharing one variable, these 5 threads would be sharing one variable. We'll cover that for later. So let's try to write a kernel to add two arrays, two 1D arrays. Let's just delete those cells. Function array add of A, B, C. So we'll need to identify each thread. So it's tidx equals thread idx of x. And since these are 1D arrays, I'll also make my kernel call 1D, which will make it easier. The basic concept here is to map each thread to some index in the array. So it will be C of tidx equals A of tidx plus B of tidx, and return nothing. And that should be it. So let's generate some random arrays. A equals rand of float32 command. Similarly, B, and then C. I mean, C need not be random, it should just be zeros in fact. So let's just make it zeros. C equals zeros of float32 command. Now remember I told host memory is different from device memory, so all these will be in the host memory. To make it easier, let's just say host underscore A, host underscore B, and host underscore C. And then the way you transfer these to the GPU memory would be by device underscore A equals ku array, CUDA array, and of h underscore A. So we're using one of the packages with CUDA native is being used everywhere. All of this is done by CUDA native. Arrays is to create an array. So d underscore b equals h underscore b and d underscore c equals array of h underscore c. Or you can just do d underscore c equals similar of d underscore a. So we'll have random arrays in the host over here, which get converted to random arrays in the device. And so now we just have to call the function array add of d underscore a, comma d underscore b, comma d underscore c. Don't forget to mention it's a good thing. And threads would be n. Zeros is not defined. I think it was zeros. Yeah, it just ran and I didn't print anything, so we won't get any output. Let's check our output. After that, let's just do it in user. H underscore c equals array of d underscore c. So we're transferring the data back from the device to the host. And we'll just use add test is approx h underscore c of, just check if they're approximately equal. So using add test, so there's nothing to add actually. Add test not defined. Oh, there was a package, my bad. Okay, we're still getting this error because I didn't run this cell again, so it basically didn't add the test body. And on running, I get test passed, so this worked proper. Now what if I wanted to launch 1,000 threads? It would still work fine. What about again now 2,000? I can't launch 2,000 threads, so I'll have to divide it. So it'll be blocks equals 2, threads equals 1,000. Now this is bad because these don't depend on n anymore. They are just constants. So let's try to keep it in terms of n. And here it would be n of int comma n by 1024. Sorry, this would be 1024. So I'm launching the maximum number of threads possible. And if n is larger than that, I launch just enough number of blocks. So we have to change this over here. So block idx equals block idx of x. Now I'll need a proper index. So it would be bidx into block dimension of x plus tidx. Block dimension of x basically tells the number of threads in that block. So if you think about it, thread 1 and block 2 would now be index 1025. And since Julia is one index, we are going to have to make this one small change so that the first thread in the first block is actually index 1. And now this would be index index, index. That should work now. Unspecified launch failure. Oh yeah, right. So we did C of index equals F index plus B of index. Here we are launching a total of 10, 24, and 2. So that's 2048 threads. And there are just 2000 elements. So 48 times there's going to be a seg fault because we are accessing out of the array. To take care of that, we can either put an if condition like if index less than or equal to size of A. But that's just boring, and there's a simpler way to do it. It's just at n bounds, which takes care that everything is happening inside the bounds. So let's run that. Right, another thing. Once a seg fault happens, usually unspecified launch failure, usually it means a seg fault happens. When that happens, the CUDA environment of this program is disrupted, and so you'll have to restart the runtime. So if you restart the runtime, everything is basically gone. It shows restarting, initializing, and once it's done, you'll just have to run all the cells again. Go using this. This one's going to throw an error again. Just run all of those and wait for the output. And yeah, the test passes. Okay, so now suppose what if I had a huge number of array elements. Remember there was a limit on the number of blocks you could launch, which is 65,000 something. So 65,000 into 1000 is huger than that. So what do you do then? You can't launch multiple grids. You can just have indexing among grids. So in that case, one thread would have to compensate for two threads. So one thread would have to add for two indexes. Uh, to make it simpler, let's just say I have 2000 and I have to manage with one block whatsoever. So what would happen is some of these would have to add for two indexes. So there won't be a need for any block index, and that's fine. So the way we do it would be take something called stride, which would be block dimension of x. And now one thing has to do for many things. Suppose it was not 200, it was 10,000. It was some random number. You can't just tell exactly 2, exactly 3. So we'll need a for loop. So it's going to be for index and one stride length of the underscore a. What this means is for the first stride elements it will do this, and then everything will be stride plus 1 stride plus 2 stride plus 3, and then everything will be 2 into stride plus 1 stride plus 2 up until length of d underscore a. Sorry, my bad, this is not 1, this is tidx. So it will be tidx for the first time, for the second time it will be tidx plus stride, third time it will be tidx plus 2 into stride. So basically from 1 to stride, then stride to 2 times stride until we reach length of d. This will be done. And that's it. And again, inbounds will help us compensate for any extra stuff. Let's run it and check. And we get an error. Invalid IR error. Oh, sorry. This is just A, not B. How I found out that was how does you come here? It says stack trace and 12 for the 12th cell, fourth line. There's something wrong with this line. You search around a bit, you'll just find that. Run the test pass. So you're able to add 10,000 elements using just one block. So any number of elements can be added using a limited number of blocks. And to benchmark this, you just have to do at benchmark along with that CUDA. And if okay, I didn't add the package benchmark tools package that add benchmark tools. So run that and that. Just run that again and wait for this to run. So you get the output. Or if you just want the time, you can make it at B time and run it. And you get the output. Make sure that this at benchmark or at B time is the last line in the cell, because once you run a cell, only the output or the result from the last line is printed and none of these is printed. For example, if you just comment that out, you get an output denoting DC. Okay, and after that you can just test. Another suggestion, not a suggestion actually, thing to be followed is you shouldn't actually use benchmarking along with testing. Because while the benchmarking, what happens is that benchmark tools runs the same function over and over again. You should kind of realize that from the output of benchmark, you get a mean, median, maximum, minimum. So the same thing is being run again and again, mean, median, minimum. So in this case, it's fine because each time you're doing C equals something. But suppose it was C plus equal to, or it was C into equal to just 2 times of A into B. In that case, this value of C would be updated again and again. So first time it would be A plus B, second time it would be 2 times A plus B, third time it would be 3 times A plus B. And in the end, when you do test, it would go all wrong. Let me just show it to you. A. Mm, I'll just remove that entire thing. A of index into equals 2. So I'm just multiplying each thing by 2. And I don't need this. I don't need this. I need that. I need this. I need this. One of these. So if I call that, I get an error. No matching method array add of CUDA array. Oh yeah, I updated here, but I forgot to run it. Running the cell updates the code. Don't forget that. So now if I run, I'll be getting the benchmark output. And after that, if I test, it should fail. Yeah, it failed because 10,000 samples. So it was run a huge number of times and the value was updated again and again and it just went wrong. Oh, no, I'm sorry. Supposed to do D underscore A. Now let's try. Yeah, it still fails. Okay, what am I even checking for? H underscore A into 2 comma H underscore C. Yeah. Okay. So it fails. That's that. So be careful while writing or modifying code because now it's going to be pretty hard to debug when something goes wrong because there'll be so much happening at once. It's hard to keep track of what's going wrong. And that's it. Thank you.